Now, in this next subsection, we're going to be looking at how to construct confidence limits and two-sided confidence intervals for a population proportion. Now, we know that for large N, we know that this standardized version of p hat, so p hat minus the mean of its sampling distribution, which is p, divided by its estimated standard error. It's estimated because we've got estimated values of p in this expression in the denominator. That for sufficiently large sample sizes, we know that this standardized version of p hat is approximately standard normal. And so because of that, and again using these kinds of arguments that we've used in the past in constructing confidence limits, we know that the probability that we get a hold of a sample for which this random variable here on the left-hand side of the inequality is less than or equal to p, the true population proportion, we know that that probability is approximately 1 minus alpha. All right, so this left endpoint here, or the left side, this expression, this random variable on the left-hand side of the inequality is p hat minus z sub alpha times the square root of p hat times 1 minus p hat over n. All right, so that probability implies that in repeated sampling, the random variable given by that expression that I just read off, the p hat minus z sub alpha times the square root of p hat times 1 minus p hat over n, in repeated sampling, that random variable will be less than or equal to the population proportion p, approximately 1 minus alpha times 100% of the time. So again, we're thinking here in terms of the relative frequency of probability. And so that means that the population proportion p, whatever it happens to be, will be greater than or equal to that random variable, approximately 1 minus alpha times 100% of the time. And so because of that, we call this random variable that we've been talking about here a 1 minus alpha times 100% lower confidence limit for p. Now, once we have our sample, once we've calculated this lower confidence limit, what we say, the way that we describe it is that we are 1 minus alpha times 100% confident that p is greater than or equal to this lower confidence limit. So that is the interpretation that we apply to this lower confidence limit. This is how we calculate it, but this is the interpretation that we apply to it. Likewise, we can go through the same kind of calculations to get an upper confidence limit for p with a 1 minus alpha times 100% confidence level. All right, so I won't read through all this whole thing again, but you know how this works now. All right, so the only difference between this and the other endpoint is now we're adding this margin of error instead of subtracting it from p hat. So once we have our sample, once we have the value of this upper confidence limit for p, then the way that we can interpret it is that we say that we are 1 minus alpha times 100% confident that p is less than or equal to this confidence limit. Now again, what that really means when we say that we have this level of confidence, what that means is that we are using a procedure that has a probability of 1 minus alpha of obtaining a sample for which this random variable is greater than or equal to p. So that is how we think about this. And then we can construct a two-sided confidence interval for p as well. And so here is the formula for that. And so if we summarize these results on a single slide, we have formulas for constructing a 1 minus alpha times 100% lower confidence limit for p, a formula for calculating a 1 minus alpha times 100% upper confidence limit for p, and then the formula for the endpoints of a 1 minus alpha times 100% two-sided confidence interval for p. Okay, let's look at an example. In a pre-election poll, using a random sample of 150 voters, suppose that 84 favored candidate Smith, so that the sample proportion p hat is equal to 0.56. And so, well, what we want to do here is construct and interpret a 97.5% lower confidence limit for p, a 97.5% upper confidence limit for p, and then a 95% two-sided confidence interval for p, where p is the proportion of voters in the overall population that favor candidate Smith. Again, let P be the proportion of voters in the population that favor this particular candidate, candidate Smith. Then a 97.5% lower confidence limit for P is given by P hat minus Z sub 0.025 times the square root of P hat times 1 minus P hat over N. All right, so P hat is 0.56, so that goes there, and then we have 1 minus P hat, so 0.44. And then the sample size is 150, don't forget that. And then our interval coefficient, Z sub 0.025, which is the upper 2.5 percentage point of the standard normal distribution, that is 1.96. And so we get a 97.5% lower confidence limit for P, that's equal to 0.4806. A 97.5% upper confidence limit for P is obtained by just adding this margin of error instead of subtracting it from P hat. All right, and so we get a 97.5% upper confidence limit for P of 0.6394. So let me go back to the previous slide for a second. How would we interpret this 97.5% lower confidence limit for P? Well, we could say that we are 97.5% confident that the true proportion of voters who favor candidate Smith is somewhere greater than or equal to 0.4806. Then, to interpret the 97.5% upper confidence limit for P, we would say that we are 97.5% confident that the true proportion of voters who favor candidate Smith is less than or equal to 0.6394. All right, now let's construct a 95% confidence interval for P. All right, and so again, I'm going to use the formula here, but we know that since we've already got these 97.5% individual lower and upper endpoints for P, if we put those together they would comprise a 95% two-sided confidence interval for P. So using the formula on the slide that we had previously, the 95% two-sided confidence interval for P, the endpoints are given by P hat minus plus our interval coefficient Z sub 0.025 times the square root of P hat times 1 minus P hat over N. And so we get 0.4806 for the lower endpoint, 0.6394 for the upper endpoint. So interpreting this interval, we would say that we are 95% confident that the true proportion of voters who favor candidate Smith is somewhere between 0.4806 and 0.6394. And now let's look at the next topic here in the context of confidence interval estimation. So how big of a sample do we need in order to estimate a population proportion with a given margin of error? And so that's what we're looking at here. And so the formula for the margin of error for a 1 minus alpha times 100% confidence interval, a two-sided confidence interval for a population proportion, is given by this expression that we've been subtracting from and adding 2 P hat. So Z sub alpha over 2 times the square root of P times 1 minus P over N. Now, I've got the true values of P in here, all right, because we need them there for right now. We're not going to have a P hat until we have a sample, and we're not going to have a sample until we know what the sample size to take. So this is actually the true margin of error associated with P hat. And if we look at just the value involving the square root, that value involving the square root is the true standard error of P hat. Right? But again, when we're trying to estimate P, we don't know P, and so we're not able to calculate the true value of the standard error of P hat. So that's why we, in the previous formulas, plug in P hat here. But for this particular derivation, we need the true values of P in here. So this is the true margin of error associated with P hat. And what we want to do is we want to find the sample size that will give us a specified margin of error for a given confidence level, which that information is contained in alpha because the confidence level is 1 minus alpha times 100%. And so we take this equality, this equation, and we solve it for n. And what we get when we do that is that the sample size is given by the square of the interval coefficient that we would use for that particular confidence level, times P times 1 minus P over the desired margin of error squared. Now, the problem with this formula is that it involves P which is unknown because that's what we're trying to estimate. So we don't have a value of P. We don't know the value of P, the true value of P to plug in here. But there are two things we can do. Perhaps if we have a previous information from this population, so maybe we have a pilot study, and we've been able to obtain a value or an estimate of P based on that, with the idea that we're going to get a larger sample and get a better estimate. Then we can plug that estimate in for P here. But in many cases, we're not going to have a prior estimate, or we're not going to want to do that. We're going to want to not impact our sample size calculation by that kind of an approximation. So what we can do is realize that this sample size, obviously it depends on P, the true value of P, but when we think about the fact that P ranges from 0 to 1, this quantity P times 1 minus P, as P ranges from 0 to 1, is going to attain a maximum value when P is equal to 1/2. When P is equal to 1/2, this quantity takes a maximum value of 1/4. Let's think about this just a little bit more. If P is 0, then the whole thing is 0. If P is 1, then this part is 0, and the whole part, and this whole expression for n is 0 again. But then as if P is bigger than 0 and less than 1, then P times 1 minus P is going to be positive, and it's going to vary. And the maximum value that it attains is 1/4, and that happens when P is equal to 1/2. So what we're going to do in using this kind of a formula is we're going to take a conservative route, in the sense that we are going to obtain the largest value that would be required in order to come up with an estimator of P with the desired margin of error. And that happens by plugging in 1/2 for P there and there. And so that's where we get this 1/4 in this expression. If we take P to be 1/2 here, and then P to be 1/2 there, okay, then we get this stuff times 1/4, and so we have 4 downstairs. So that is where we get this formula. So this is going to be the sample size that the formula that we use to obtain the sample size that will ensure us really a margin of error of no more than E, cap E, when we're trying to estimate a population proportion at a given level of confidence. So let's look at an example. In close elections between two candidates, that is when P is close to 0.5, a pre-election poll must give rather precise estimates to be useful. Suppose that we would like to estimate the proportion of voters favoring a certain candidate using a 95% confidence interval that has a margin of error of no more than 1%. And so what sample size would be needed? All right, and then we'll also look at if a confidence interval with a margin of error of no more than 3% was desired, what sample size would suffice. So let's answer these two questions. So if we wanted to come up with a sample size that would guarantee that the margin of error associated with our estimator of P was no more than 1%, then so cap E in this case is 0.01, and so we would plug that in the denominator, and we have to be sure to square that. Don't forget that, that's a common mistake. For a 95% confidence interval, the interval coefficient, the z-value, z sub 0.025 in this case, would be 1.96. So we have to square that as well. And so this formula will give us a sample size. Now, remember that if it gives us a fractional value, then what we need to do is go up to the next larger integer. All right, and so anyway, when we do this calculation, we get a sample size of 9,604. So if we obtain a random sample of 9,604 voters, then we will get an estimate of the true proportion of voters who favor a particular candidate, and that estimate will have a margin of error of no more than 1%. Now, in reality, the margin of error may very well be quite a bit less than 1%, if P is quite a bit different than 0.5. But if it's close to 0.5, then the margin of error should be about 1%. Now, that's a large sample size, and we may not have time or the resources, financial resources, manpower resources, and so forth to select a sample of that size, at least in a short time frame. And so maybe instead of a 1% margin of error, perhaps a 3% margin of error would suffice. And in fact, that's a common margin of error used in public opinion polls. If you have seen articles or results online or in magazines or in newspapers regarding or reporting polling results, if you look in the fine print, then most of the time they are going to have used, the results will have an associated margin of error of 3%. And so if that's the case, the only thing that changes in our calculation is cap E, right? It's equal to 0.03 now. And so when we do the calculation, we get a value of 1067.1. Repeating, since we have a fractional value, we'll go up to the next larger integer. And so we would use a sample size of 1068. So, if you think about, maybe in the context of a presidential election or something like that, where you've got millions and millions and millions of registered voters. And, we want to estimate the proportion of those people who favor a particular candidate, then it doesn't take that large of a sample, compared to the size of the population in order to estimate that proportion to within 3%, or even 1%, really. I mean, 9,000, 9,600 is not that big compared to millions, millions and millions of voters. But anyway, if we were to select this a random sample of size 1068, then we would get an estimator of the true proportion of voters who favor a particular candidate with a margin of error of no more than 3%. All right, so that wraps up this segment on inferences for a population proportion.